Okay, class. We don't have a lot more lectures to go um, for, basically the end of the lecture segment of the course. And I have no way of thinking about how we can do labs, although I may send you out something where you look at a simulation somewhere on YouTube or whatever to see how you could use PSpice, or what is the analog to PSpice, or the follow-on, I should say, to PSpice. But that's not what we're doing today. What we're doing today is we're going to look at decibels and decibel attenuation and decibel amplification, and see how that manifests itself in all types of wave communications, whether this be decibel or acoustic decibels, or whether it's electronic, waveform decibels, comparing the amplitude, or in our case, the voltage to, different places. Let's say that I was going to put a signal that was at 100 megahertz over a coaxial cable that was 1,000 meters long. What would the voltage, if I put in a voltage at one end that's 100 millivolts peak to peak, what's it going to be at the other end? Right? And so really, when we're talking about decibels, we're talking about attenuation, and we're talking about attenuation of power. So we've got something that starts off like this, and then it gets smaller and smaller as it goes along, right? So we're attenuating the signal's power. So this would be power, and this would be distance that the signal is traveling over. Let's say that this distance out here is 3 kilometers, right? And we start off with power that's something like 1 watt, and then way out here we have something that's 1 milliwatt, or whatever. I'm just saying that it's the decay of power of the signal over a distance. We could say the same thing is true about acoustic noise from a jet engine, right? If I'm standing right next to a jet engine, that's pretty loud. If I'm far away from a jet engine, it's probably a lot quieter. And why is that? Because the atmosphere has attenuated the acoustic signal, which are, compression waves of the sound coming to my ears, right? Of course, when a plane's flying over your house all the time, that can't be good. All right, so really what we're talking about today is decibels. And we're still having at least one more lecture that's going to be on series and parallel AC circuits, and how to work out the impedance for all of the various different components in those circuits, and figuring out what the voltage is at different places in those circuits. And it's not going to be something that where you have to use mesh analysis in complex numbers, but it's going to be something where you have to figure out which of the components are in series and which of the components are in parallel, and which other components are in series with those components that are in parallel. Do you know what I mean? All right. So anyway, let's get down to decibels. And because these are things that you're going to run into, as a mechanical engineer, obviously you're in the field of acoustics, right? So decibels, acoustic decibels are going to be something that you're going to be working with. And these apply, what I'm teaching you here today applies as well to that as it does to electromagnetic signals traveling down a wire. All right, because really decibels are just power. And I think that we did talk for a little while in class about what decibels were. I don't know if I gave you a whole class. I may have just given you an introduction to what decibels are. Anyway, to talk about decibels is to talk about log functions. And so let's look at a couple log identities, right? So the log of A times B is equal to the log of A plus the log of B. All right? And the log of A divided by B is equal to the log of A minus the log of B. And when we look at the log of x to the n, log of x to the n is equal to n times the log of x, right? So does everybody see all of those things? Now, if I want to know, when I'm talking about the logs here, every time I write a log where it has no subscript, I'm talking about log to the base 10, right? So let me just use my disclaimer here. Log equals log to the base 10. So that I don't have to keep writing to the base 10 with this large marker that's calling itself a fine point marker. Really? I don't think so. So I want to show you another. So we're always talking about log to the base 10. What if I wanted log to the base 2 of x? How could I find that? Right, log to the base 2 of x. For instance, what's log to the base 2 of 4? Well, isn't it 2 to the 4, 2 to the 2 equals 4? 2 squared equals 4. So log 2 of x, of 4 would be 2. Log 2 of 8 would be 3. Log 2 of 16 would be 4, right? So on and so forth. Everybody knows what log 2 to, whatever, log 2 of 256 would be 8, right? And so what you really have here is you have log 2 of 10 times log to the base 10 of x. You're probably saying, well, what is log 2 to the base, log 2 to the 10, well, what, 2 to the what equals 10? And that's a good question, isn't it? Because we could write that right here, 2 to the what, let's call it y. 2 to the y equals 10. Well, what is y? Well, here's how we can find it. We can use our identity right up here, log x to the n equals n times that. We can just do it to this side, right? Because that's y. So we could say that y times the log to the base 10 of 2, because we've done that to that side, is going to equal log to the base 10 of 10. And log to the base 10 of 10, let's see, 10 to the what equals 10? Yes, that's right, 1. 10 to the 1 equals 10. So then we find out that y is just equal to 1 over the log to the base 10 of 2, right? I'm just using my identities that I've got up here. And of course, that comes out to 3.322. Is that the true value of pi? No, of course it's not. Because it's got 3 in it? Come on, please. All right. Now, do you understand all of my logarithmic identities that I've put up here? Because that's important for our lecture on decibels today, right? That's what we want to see. We want to use those, but we also want to understand what decibels really are. Decibels are a power ratio. And as you know, power, there you go. I'm getting COVID-19. I hope not. I've been like locked in my place for days and days, but I have had people deliver stuff too. I didn't wipe it off with a Clorox rag. Or I might just need a little drink. I think I'm still recording. Anyway, let's get back to decibels. So here's what the equation for decibels are. A decibel is 10 times the log to the base 10 of the power out over the power in. That's it. See, isn't that easy? Now, that would be easy if we had a power meter for everything, but we don't. We have a voltmeter for everything, don't we? So what is a decibel in terms of voltage? Well, let's look at that. Well, 10, and then let's look at what we've got here. Now, that's going to be the log, and what is power? I'm going to make this a little bit bigger. What is power? Well, we've got a couple equations for power, don't we? Power equals I squared Z. Power equals IV. And power equals V squared over Z. Yep, we're up to Z now. We're not using R anymore. V squared over Z. So what we really can say here is I've got V out squared over Z divided by V in squared over Z. Right? So don't the Z's cancel out? That's right. So the Z's cancel out. So I really have V out squared over V in squared. Well, hey, doesn't that equal 10 times the log of V out over V in, the whole quantity squared? That square's in here, not in that other box. I better redraw that line. Sorry. Well, that's perplexing, isn't it? So let's see what a decibel is in terms of voltage. Well, we've got that 2 up there. You know, I've got 10, but then don't I have that 2 up there? If I've got log to the V out over V in squared, just like I've got up here, let's call that equation A, right? Couldn't I take the 2 and bring that down in the front and then have the log of V out minus the log of V in? Or excuse me, have log of V out over V in? So let's do that. So there's the 2, and now I've got the log of V out over V in. Does everyone see how that works? So, in terms of voltage, decibels are really 20 times the log of V out over V in. And we can very quickly determine what the voltage is, even though it would be much harder to determine what the power is, right? Does everyone see that? So that's my equation. I'm going to just circle this so that we know that that is decibels. Now, that's not all, that's not the end to decibels, by the way, because there are a couple what I would call conventions for decibel so that we can compare apples to apples and oranges to oranges. When we first, first decibels came into wide use was really during the telephone age, right? Because they had to know how much the signal was falling off. Even the telegraph age, they had to know how much that signal was falling off, although it was much more important for telephone. How that signal fell off over distance, right? And so they wanted some type of standard like, oh, it's fallen off 50 decibels. So that'd be minus 50 decibels attenuation rather than plus 50 decibels amplification, right? So that's what we really want to see here is what do we really have? Let's say that we had a power differential. Let's just do a little example problem. All right. So let's say that I have a 10-kilometer long coaxial cable, right? 10 kilometers. And I put a signal in one end. And the signal that I'm going to put in at that one end is going to be a power of 1 watt. And what comes out the other end is going to be 1 microwatt of power. Let's just look at it that way. So I've got 1 watt going in, and I've got 1 microwatt coming out. How many decibels? Now, would that be an attenuation or an amplification? I think everybody can see that it's going to be an attenuation of the signal over this 10-kilometer long distance, right? And of course, really the signal fades off not linearly, but exponentially. So actually polynomically. But let's look at this then and see what how many decibel attenuation that would be. So decibel attenuation is going to be 10 times the log of the power in, which is 1 watt, divided by the power, or excuse me, the right off the bat, I put them upside down, don't I? I'm showing you an attenuation. I want it to be negative, of course, and I did it upside down. Hey, caught myself pretty quickly there, though, didn't I? So 1 microwatt is my output, and then 1 watt is my input. So that's 10 to the 6th, isn't it? Right? Log base 10. I've got 10 to the minus 6, because micro on top. It's going to be minus 6, and this is going to be 1 on the bottom, or 0. So it's going to be a 6-fold increase. So this is going to be minus 60 decibels. You see where the minus comes from? The minus means that it's attenuating the signal. It's taking it from 1 watt at one end and taking it down to 1 microwatt at the other end. So it's attenuating the signal. Now, let's say that for the second problem, I have something that's taking an amplification. I want to amplify uh, a power in a circuit. And so I amplify that, and the only way that I can really read that is with voltage. So I know that the signal that's going into my amplifier is going to be 1 micro volt, right? So I know what's going in is going to be 1 microvolt, and I know what is going to come out is going to be 1 volt. And you're probably saying, hey, it's 10 to the 6, just like that one. It's going to come out to the same thing. No, of course it's not. Of course it's not. Or else why would I do it? Right? So let's do that one now. Now the dB amplification, this is an amplification, right? Because I go in small, I'm coming out large. And that's going to be 20, isn't it? Because the 20, don't you remember when I've got the 20 down here instead of the 10 for power, 20 for voltage? So that's going to be 20 times the log of V out, which is 1 volt, divided by 1 microvolt, right? So instead of that, the amplification that I'm really going to be having there, because this is going to be 6, isn't it? 6 times 20 is 120 decibels. And of course, that's positive because it's an amplification, not an attenuation. And wouldn't that be true? Because if you look at the relationship between power and voltage, it's squared, isn't it? So you can see that this, because it's a logarithmic function, is instead of it being squared, it's going to be doubled, right? It's going to be doubled. Now, there's also other conventions that are out there, and I'm going to give you some of those. dBm. dBm is a standard that the telephone companies in the 20th century used a lot. And the way that you look at it is 10 times the log of whatever power out, right, over 1 milliwatt. So if you were working entirely in dBm, everything would be standardized to 1 milliwatt. Do you see what I'm saying? So it's basically like measuring voltage with respect to ground. You've now got everything referenced to 1 milliwatt. So all of your technicians, as long as they've got their dBm meters, and the dBm meter always reads the same thing, or relative to 1 milliwatt, they can all speak in the same language. Now, when the fiber optic industry started to come in and take care of the trunk, or take over the trunk lines and everything, the dBm changed to dB mu, right? Which is going to be 10 times the log of P out over 1 microwatt. And of course, that really symbolizes the difference in power per bit of information that's being transferred. 1,000-fold power efficiency, productivity, you might call it, for transmission of signals when we started to replace the old copper wire backbone with the new fiber optic backbone. So you can see that too. How do we really, look at decibels? And in fact, if I had a graph, well, let's put it down here. If I had a graph and decibels were up here, and of course, you've got to remember decibels is a log function, right? And then I had the log of the frequency down here. What do I really have? Don't I really have a log curve? Don't I have a log curve there? And so when I look at, if you remember, I drew, let's say, a low pass filter for that RC. Oh, and by the way, all of this is in chapter 21. I'll write it right here, chapter 21, and I would like you to just read the first couple sections in chapter 21. It goes on to talk about the intricacies of an RC filter. But we don't really, you can read that. That will definitely enhance your understanding of the RC circuit, which you may see on the final. I'm going to, use that as a disclaimer. You may see that, you may not, but you may. And so read chapter 21, so that when we saw that low pass filter, remember what I was talking about with the RC circuit. So this is an RC low pass, that's low pass filter. And you can, you can see that in, I think it was chapter 16, was it 17? I don't know, 16, I think. And then you can also see it talks about the RC there, but you can also see the RC filter talked much more in chapter 21 if you want to do that. Now, when we look at this from this perspective, what we see is this. That's what this looks like on a log graph. That's right, straight lines, right? Now in actuality, it's not exactly straight. It really looks something more like this. Right? It looks something much more like that in reality, but in theory, it would look, this is what we're going for, because that slopes down, and because this is logarithmic, and because this is logarithmic, we get something that looks like this. So when you look at a band with a band pass filter or anything, whether, whatever you're looking at in relationship to frequency, and let's say this would be the voltage at A, or the voltage across a capacitor or whatever, then you're going to see it look like this. But then if you, this is called a Bode plot, where we got the dB attenuation. And then where is this? Remember originally I told you that that the voltage at A would fall to 70.71 volts, right? And that was at that magic frequency that we called the um, for the RC circuit, the resonant frequency for the RC circuit. And what is that drop off? 70.71 volts. Let's do that, shall we? So dB equals 10 times the log. Now my output, right, is going to be 70.71 volts, and my input was 100 volts. Wait, did I say 10? I meant 20. There we go. So dB of, let me just do that, although I already know the answer, 70.71 divided by 100 equals log times 20, voila, minus 3.01 decibels. Now you might say minus 3.01. I thought it was supposed to be minus 3. Well, whatever. I get minus 3.01 on that calculator. But there you go. And that is the thing. That's where it is. When you're talking about an attenuation in a filter, whether it's a filter like this or whether it's a filter that would be more a band pass filter, something like this, right? Where only these frequencies get through, like a radio station, right? In fact, that's how they do it for a radio station. They have a filter there that only lets the radio station frequency get through and wipes out all the other frequencies around it when they're broadcasting a radio station, or when your radio in your car is tuning to the radio station. It's just picking up that frequency. It's using its bandpass filter to get that frequency. Okay, that's going to be the end of my lecture for decibels. We're going to do one more lecture, I think, on, like I say, series and parallel components in an AC circuit. And that'll be about it for the class. And then I'm gonna have you do some other stuff too, like, look at a simulation, or actually a YouTube video that I really like about how to use OrCAD, Multicad, or PSpice, whatever you want to call it. All right. Well, thank you for watching, and I hope that all of your other classes are going well too, and that you're staying safe and you're not infecting your parents.